organizers for giving me the opportunity to attend this great summer school and also to give a talk and present recent results on the regularity of SPDEs in a certain scale of Besov spaces which is closely related to nonlinear approximation. What I will present today is joint work with all the people listed here who work together with the overall goal to design adaptive wavelet methods for solving SPDEs, as well as with two of the organizers, Professor Kyung-Kun Kim and Professor Lee. Today I will start by presenting the scale of Besov spaces, which is commonly also known as the adaptivity scale, and then I will spend maybe the half of the talk by explaining why it is called like that and why we are interested in the regularity of SPDEs in this scale of Besov spaces. Then I hope I have enough time to present the results we have for the regularity in space first and then in time, and then at the end I will summarize my talk and give a short outlook. I will restrict myself in this talk to the heat equation with additive noise as a model equation. Although all the results I will present are also valid for a wider class of second order SPDEs. I use the same setting as Professor Krylov and Professor Gyung use in their lectures, with one main difference. We are interested in solving these SPDEs on bounded domain with Lipschitz boundaries, so non-smooth domains, with zero Dirichlet boundary condition. Now, if a solution exists, or better, if a solution exists, then a version of it is just a function depending on three variables, omega, the time t, and the space variable x out of our domain. And usually one splits the analysis of the regularity into two steps. First, we analyze the regularity in space, which actually means we are searching for appropriate function spaces and try to analyze if our solution lies in these spaces for almost all omega and t. And if we are successful, then the solution can be solved as a process taking values in this space, and then we analyze the regularity in time, meaning we look at the path of this process and look if they are either continuous or anything else. Now it's common to use the Sobolev scale to analyze these spaces, or on domains, rated Sobolev spaces fit much better. We have seen yesterday in the talk of Vildu a very nice overview over the work in these spaces. However, we are interested in another scale of Besov spaces, namely this one is called the adaptivity scale. The smoothness parameter alpha and the integrability parameter tau are linked by this equality, and p is a fixed number greater than or equal to 2, and we want to tackle these two problems in this scale of Besov spaces. Now, since they are not that common as Sobolev spaces, I first want to introduce what Besov spaces are. I used the definition by differences. There are at least 5 others, equivalent definitions. So we have two parameters, q and nu, both greater than 0 but finite, and denote by r the least integer strictly greater than nu. Then a function u, which is a q integrable on our domain, is said to be in the Besov space of smoothness parameter nu and integrability parameter q. If this quantity here stays finite, let's look at it. If we drop this part, then we have just dt over t, because the behavior of 1 over t at 0, this is not finite. If we multiply it by t at the power minus nu times q, it's get even worse. So this quantity here, which is also called modulus of smoothness, has to go to 0 in a fast way such that this integral here becomes finite. And this modulus of smoothness is defined by differences, which are defined iteratively by this formula. Now, these spaces are normed by the Q norm plus this quantity, and if Q is greater than or equal to 1, then we have Banach spaces, but if Q gets smaller than 1, then we're dealing with quasi-Banach spaces, so the triangle inequality doesn't hold anymore, just with a constant. And the things get a little bit more complicated, and if we look at our scale and we are interested in high regularity, so alpha gets bigger and bigger and will become, so that this tau here will become less than 1, and so we're dealing actually with a scale of quasi-Banach spaces. Yes. Now after we have seen which scale we want to use, let's see why we want to use it, and therefore we have to talk a little bit about approximation theory. So we want to approximate the target function u out of L2, so what we do to design a scheme, we take a sequence of subsets of L2 in each step and take a function out of the subset, and this will be the approximation to our target function in step n. Now, capital N stays for the amount, for the number of degrees of freedom we have to fully describe this subset. And we can differentiate the methods of approximation into two classes. Namely, if we choose these spaces Vn to be linear subspaces, we're talking about linear approximation. We denote the error here in the talk by En all the time, and we measure the error in the space where the target function lives. This is the minimal error we will do. But it turns out that sometimes it's very useful to choose these subsets in such a way that they are not linear subspaces anymore, so that, for example, the sum of two elements of Vn is not again in Vn, so we don't have a linear structure. Then we're talking about nonlinear approximation, and we will denote the error we make, the minimal error, by this. So when we're solving an equation, we refine in each step our space where we solve the solution, and we can do this in two ways. We can, on the one hand, we can do it uniformly. We have seen uniform method presented by Professor Gyung and also in Eric's talk. In the language of finite differences, this means in every step we refine the grid on all of our D uniformly. Then we're talking about uniform methods, and the benchmark for the convergence rate of these methods is given by the convergence rate of linear approximation methods. On the other hand, we can refine our spaces adapted to the target function and look to the behavior of the function and refine, for example, our grid depending on how the function behaves locally. Then we're talking about adaptive methods, and adaptive methods, the benchmark for the convergence rate of these methods is given by the convergence rate of nonlinear approximation methods. Now, before we see how we can, adaptive methods are pretty hard to design and to implement. So before we start doing this, we should clarify if we should do this, so if we can get better convergence rate or not. And therefore we have to compare the benchmarks, so to see if nonlinear approximation can perform better than linear approximation. And before we see a criteria how we can decide this, let's see an example for linear and nonlinear approximation. It's quite simple, but I think pretty important. We have just a Hilbert space L2 and take an orthonormal basis. The degrees of freedom are the elements of the basis, E1, E2, and so on. And the natural way to do linear approximation is to take in each step the subspace Vn to be the linear span of the first n elements of the basis. then the best approximation we can do is the projection into this space, and by Parseval's identity the square of the error we make is given by this formula. But we can also do nonlinear approximation, and a common way to do it is it's the so-called best n-term approximation. There the subset Vn is the collection of all linear combination of at most n coefficients of the basis and elements of the basis, but which coefficients we use is not fixed a priori. So the error we make is given by this, and we can choose nebula star to be the index set connected to that amount of elements of our basis where our function has the highest or the greatest coefficient. So we are obviously getting something that is less than the error we make in the linear case, where we take just the first one independently where the high coefficients lie. Now let's see how we can decide which one we should use, and in a natural way it's given by the regularity analysis of the target function. So if our target function has Sobolev regularity S, then there exists linear approximation methods such that the convergence rate of the methods is minus S over D. On the other hand, for a wide class of linear approximation methods, it is also known that if we don't have this Sobolev regularity, we won't get any better convergence rate than minus S over D. The convergence rate of nonlinear approximation depends also on the regularity, but not on the Sobolev regularity. It's the regularity in this scale of Besov spaces, and if a function has alpha regularity in this scale, then the convergence rate will be again minus alpha over D. So to decide which one is better, we have to compare alpha and S, so the Besov regularity and the Sobolev regularity. Now this connection we can illustrate in a diagram named after DeVore and Untitled. Each point in this diagram represents a function space on our domain. We have here on the x-axis we have the reciprocal of the integrability parameter, so that this point here represents just the L2 space, for example. All the spaces above this space are function spaces, subspaces of L2, and we categorize them by smoothness, meaning by differentiability. So for example, this space here, this point here represents the L2 Sobolev space of order 1, and all this scale here represents the Sobolev spaces of order S, and for this parameter p equal 2, they coincide with the Besov spaces. It's a well-known fact. So because of this connection between linear approximation and the regularity in the Sobolev space, it is often called linear approximation line. On the other hand, the adaptivity scale can be illustrated by this line with slope d, and because of the connection to nonlinear approximation, it is called nonlinear approximation line. Now remember, we have the solution of the equation, and we want to decide whether we should use adaptive methods or not. We have seen we should compare first if nonlinear methods will work better than linear methods. So we have to answer two questions. How high is the maximal regularity in the Sobolev scale? So this limits our convergence rate of uniform schemes. And on the other hand, we have to clarify how high we get on this scale. And this point here will be, Felix will talk about it after this talk. And in this talk, I will present results in this scale, so that in the two talks together, we will have a partial answer on what is better. So if alpha is greater, equal, or less than S bar. Now, we also already heard yesterday that on domains, the Sobolev regularity of of solutions to SPDEs aren't that that great. It isn't that great. So Professor Krylov presented some counterexamples where the coefficients are very smooth and the domain is smooth, but the solution fails to be in the Sobolev space of order 2. So he suggested so the main reason for this is the bad behavior of the derivatives of the solution near the boundaries. So he suggested to use weighted Sobolev spaces to control their behavior near the boundary. And this has been done for parameter p and parameter greater than or equal to 2. And Professor Kim proved last year an existence and uniqueness result also on Lipschitz domains we are interested in, and this is our starting point. So I want first to present the existence result of Professor Kim and then show how the solution behaves in this scale of spaces. Therefore, I first introduced this weighted Sobolev spaces. We have three parameters. P is again the integrability parameter, gamma is the smoothness, and theta is the control of the boundary. We denote by rho of x the distance of a point x to the boundary. And for non-negative integers, gamma, the space is defined to be the collection of all functions such that this quantity here stays finite. It looks like a Sobolev norm, but with these weights inside. Notice that the weight we put inside the integral depends on the order of the derivative and on this weight parameter theta. And it is obvious that if the whole power here we put on the distance to the boundary is positive, then we dampen up around the boundary so the derivatives can blow up and this quantity still stays finite. For non-integer gamma, we can define the spaces by complex interpolation, and for negative gamma we can introduce them by duality. Actually, we presented yesterday equivalent definitions to these ones. And two-valued functions. For two-valued functions, we can define analogous spaces, and to deal with stochastic processes and with stochastic PDEs, we introduce in complete analogy to the lectures of Professor Geng and Professor Krylov these board-edge spaces, gamma p theta, to be the spaces of all predictable processes which are LP integrable over the time, and omega and take value in the weighted Sobolev space H gamma p theta. Now, in these spaces for arbitrary parameters gamma and unbounded Lipschitz domains, as I said, Professor Kim proved that for a certain range of weight parameters theta, there exists, if the coefficients of the equation have a regularity of order gamma minus 1, and we put the right weight parameter and the same for the initial condition, then our equation has a unique solution with regularity of order gamma and weight parameter theta minus p. So in this scale of spaces, we have then a full LP theory, meaning that if we raise the regularity of the coefficients, we can raise the regularity of the solution if we put the right parameters on the weight. Now, let's see what what regularity this solution has in the adaptivity scale. Here is our main result. If we restrict ourselves to gamma greater than 0, then we have this solution for the right parameters. And we can write this space by like this. If we just put S to be 1 plus d minus theta over p, and then we can say that our solution takes values in this space for all alpha in this range. So if we can now raise gamma, so actually the bound is given by S times d over d minus 1 if we have smooth coefficients. Now this result, or let's say a weaker version of this result, has been published last year. There we still have gamma to be an integer. Now we can prove it for gamma greater than 0, and there we have another assumption which now moved into the claim because it's already inside of this regularity. Now, how did we prove this? We actually didn't use the equation. We just proved that these spaces are embedded in these spaces. So we could prove this result, that weighted Sobolev spaces are embedded in the scale of adaptivity, the adaptivity scale, for all alpha in this range. So this is a pretty important result because now we can reduce the whole analysis in this adaptivity scale to an analysis in the weighted Sobolev spaces. So every result for SPDEs in weighted Sobolev spaces can be used to say how fast nonlinear approximation works. At the same time, we proved this embedding, and we actually use it to prove this embedding. And what we actually proved is that if gamma is greater than or equal to S and S is in this range, then this space is embedded in the collection of all BS, all elements of the Besov space of order S, where the trace is well defined and is 0 on the boundary. So we're really talking, in this sense, we are talking about a zero Dirichlet boundary condition. This follows past famous result of Jerrison and Keeney. Before I go on with the time regularity, let's see an example. There were pretty much parameters maybe not everybody can follow. So we have the two-dimensional case. We take gamma to be 2, so the order of smoothness. We take the Hilbert space case, so p equals 2, and we take theta to be the dimension. Now, we get from the second embedding, we get that our solution is in the Sobolev scale, is in the Sobolev space of order 1. From the first embedding, we get twice the regularity in this scale of Besov spaces. And we will see in the next talk that on Lipschitz domains, the bound for the Sobolev regularity is beyond 2. So there is a gap so that we can say, yes, we should try to implement adaptive methods because we have hope that they will work better. Now, as I said, now we know that our solution takes values in these Besov spaces, and we would like to see how the path behave of the process if we look at it as a process taking values in these spaces. And here I don't have that much time left, so just result. If we impose more integrability in time on the coefficients and on the solution, then we can prove some Hölder regularity on the path of the solution, which will be helpful in the design of the scheme in time, maybe. And we see that the Hölder exponent, if it rises, the alpha exponent has to go down. That is pretty natural. And we won't get here more than 1/2, what is also natural because of the behavior of the Brownian motion. Now, to summarize my talk, these are the take-home message, is that the convergence rate depends of adaptive schemes, depends on the regularity in the adaptivity scale of Besov spaces, and that we can reduce this analysis in this scale to the analysis of the regularity in the weighted Sobolev spaces. Then, together with the forthcoming talk, we will see that the benchmark for adaptive schemes in space is better than for uniform schemes, and we have positive header regularity. And now we are working on implementing, designing, and analyze the convergence of adaptive schemes based on wavelets. So here is some literature divided by the different topics I've been talking on. I want to thank again for this nice summer school and the opportunity to give a talk, and thank you for your attention.